Hiya. So in this video, we're going to look at directional derivatives and also an example of a conservative vector field. So as a quick recap, remember that vector field, this is just going to be some function that takes some point. So we take a point in affine space and we give it, in essence, a vector. And so what we said is, one thing is that this could arise from the gradient of some function. So we could have some function if we take the gradient. This is the partial derivatives things. Then if this vector field is equal to the gradient of some function, then we're going to call it conservative. So let's look at an example of what a conservative vector field looks like. So here we're going to define our function. So here we have f of xy is a function x squared plus y squared divided by 2. Let's do the partial derivatives because it's probably been a while since we've done partial derivatives. So here, if I'm going to take the partial derivative with respect to x, I pretend y is just some number, and I derive by x. So y, since it's a number, is going to disappear, and we bring the 2 in front of the x, so we get 2x over 2, and this is just equal to x. And we can do the same thing with y, so partial derivative of y. Here we keep x as a constant, and we derive based off y. So we end up with 2y over 2, which is just equal to y. So in other words, the gradient given by this formula is precisely x ex plus y ey. And if you recall from last video, we already had here it is. We already had a vector field, w, that had precisely the same formula. So this formula is identical. And in other words, this w is going to be conservative, because w is equal to nabla f. So w equal nabla f is why it's conservative. So generally, if you're trying to show something is conservative, you're going to be looking at finding a function that does this. So things to note is that like this vector field is going to be pointing in the direction of f, where it increases the most. So it's orthogonal to the level sets. So let's kind of see what I mean by that. So here I have the graph of f, and you can kind of see the level sets on the bottom. So like here, let's zoom in a little. So here on the bottom, over here, for example, you have the different level sets, and you're going to look at the tangent vector to this, where the direction is that f increases the most. So what direction is f increasing the most? And this is where this idea of tangent is coming from, right? So like you can kind of think of like, okay, so if this point here, if I bring up here, I look at the tangent, it's going to be pointing at this direction. Now if I look at from above, this direction is precisely, it's going to probably be some point here. So these vectors are precisely what is giving us the directional derivatives at these things. And we'll talk about directional derivative in another thing in a few minutes. But first, let's look at a different example. So we're going to look at a vector field w tilde that's given by minus y plus x. And this here we have a graph of this. It's shown here. So here on the right, this is w tilde from before. And basically we just took this value here and we plotted it at a bunch of random different points. And you can kind of see this gives like a nice little spirally shape. Okay, so the question is this conservative? So how do we know if it's conservative or not? So if it's conservative, there exists f such that w tilde is equal to nabla of f. In other words, the partial derivative of f with respect to x is equal to minus y, and with respect to y is equal to x. But as these things must commute, right? So it doesn't matter if I take the first derivative or the second one. One thing to kind of note is I can now take the next derivative and I should get the same value. So in other words, if I do df dy dx, right? So here I'm going to do the other one. So first I do x and then I do y. This gives me minus 1. Here, I'll put the minus 1 on the right-hand side. Minus 1 is equal to this. Here, this should equal to the opposite. So I should be able to switch these around. Well, this is just a 1, right? And yeah, so this is the problem because -1 does not equal 1. And so this is not conservative. Conservative. Another way to kind of see this is to basically try and go backwards to try to find the integrals. So another way to see that it's not conservative is we can take -y dx and try to go up, and this is going to give us -yx plus some constant. And then on the other side, we'll have x dy, and this is xy plus some constant. But notice here how I have -yx and here I have xy, and these two are not compatible, right? So these two are not compatible. And so here we have another problem showing that it's not conservative. So you can either do integrals to go up or you can do derivatives to go down. And both of these are a way to see whether it's conservative or not. I said I would do directional derivative in this video, but actually I'm going to save that for the next video. So in the next video, I will talk about directional derivatives. So I will see you then. Have fun.